Hi, so now we're ready for section 4.2, graphs of exponential functions. They want us to start off by just graphing these kind of generic exponential functions by plotting points. So in this first one here to the left, let's make an XY table and plug in values -2, -1, 0, 1, and 2 for our X values. So if we plug in -2 for our exponent, remember a negative exponent means reciprocal. So that would give us a 1/4. 2 to the -1 is 1/2. 2 to the 0 power is 1. 2 to the 1 power is 2, and 2 squared would give us 4. So what would this look like if we graphed it? So X is -2, 1/4, -1, 1/2, 0, 1, and then 1, 2, and 2, 4. Notice how it starts to increase pretty quickly. So if we're to graph it on just that side of the points, notice how it increases. But the question is, as the graph goes to the left, will it ever be 0 or negative? In other words, is there any exponent that if I took 2 to that exponent, would it ever be less than or equal to 0? The answer is no. Notice when we plugged in 0, we got a +1. When we plugged in a -2, we got a +1/4. Those negatives only change the position. It takes the reciprocal. So this function will continue getting closer and closer to 0, 1/4, 1/8, and so forth, but it will never actually reach 0. So this would be a no. Let's take a look at the next one. Here, our base or our factor is 1/2, so we have a decay factor. We create an XY table. Let's use the same X values. -2, -1, 0, 1, 2. Again, the negatives mean reciprocal. So if we take the reciprocal of 1/2 and square it, we would get 4. 1/2 to the -1 is 2. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. And 1/2 squared is 1/4. So what does this look like when we graph it? We have -2 up here at 4, -1 at 2, 0 at 1, 1 is at 1/2, and 2 is at 1/4. And it's the same concept, just decreasing instead of increasing. It will never hit 0 or become a negative unless there's some vertical shift. So these are parent functions. We're not adding anything to it. There's no a in the front. So all of those generic functions would look similar to these two. So we want to take a look at the characteristics of the graphs of this parent exponential function, f of x equals b to the x, when the base is greater than 0, but doesn't equal 1. Try to minimize that so you can see both at the same time. Are these functions? Yes, they pass the vertical line test. They're also one-to-one functions, so we can deal with inverses. They both have a horizontal asymptote at y equals 0. There is no vertical asymptote. The domain, we can plug anything for the x, so it goes from -infinity to infinity, but the range starts right after 0. So we're going to use parentheses 0 all the way up to infinity. There are no x-intercepts, since it doesn't cross the x-axis, and the parent function has a y-intercept at 1, so we get a 0, 1 as our y-intercept. It's increasing over the entire domain from -infinity to infinity if b is greater than 1. In other words, it's more than 100%. It's decreasing on its entire domain, -infinity to infinity, if our b is between 0 and 1. We do not have a local minimum or a local maximum, nor a global min or max, and we have end behaviors for both. If b is greater than 1, in other words, it's increasing, then as x is approaching -infinity, y is approaching 0, and as x is approaching +infinity, y is also approaching +infinity. the end behavior for a decreasing exponential function, in other words, your factor is a decay factor between 0 and 1, then it's backwards. As x is approaching negative infinity, y is approaching infinity. And as x is approaching positive infinity, y is approaching 0. You don't have to memorize all of these, but it's good to review what is in behavior, what is increasing, what's domain and range, and just kind of give you an idea of what these generic equations look like. So when you do have a transformation, you're able to graph it. Speaking of transformations, so here's the general form of an exponential function where we have different pieces. So that a is being multiplied by the parent function. So that is our vertical stretch by a factor of absolute value of a. If that a is greater than 1, we have a vertical compression. In other words, it shrinks by a factor of the absolute value of a if that absolute value of a is in between 0 and 1. Now, if that a is negative, remember those negatives means that we have a reflection. If you're multiplying those output values, which are the y's, by a negative, that means it's going to reflect over the x-axis. If the x value is being multiplied by a negative, then the graph of f of x is reflected over the y-axis. Just think if you multiply those x's, x's change signs over the y-axis. Then we have this c up here, x minus c. Remember, when you add or subtract from x, that means we have a horizontal shift left or right, but it's always in the opposite direction of that sign c. Our last one, d, same thing, vertical shift, but it shifts in the same direction as d, so it's going to go up or down. Remember, the rules for transformations are all the same. They just look different because you're dealing with different parent functions. In this example, we want to use transformations to graph the function f of x equals -2 times 3 to the x plus 4 minus 1. Well, our parent function would be 3 to the x. So we can graph that one first, maybe dotted. You can do this if you still want to, the -2, -1, 0, 1, and 2. To the -2 power would give us a 1/9, so really small here. To the -1 would give us a 1/3. To the 0 power would give us 1. But then to the first power would give us 3, and squared would give us 9 up here. So I'm going to dot this guy. That's our parent function, just 3 to the x. Now let's take a look at what's happening to this parent function. It's being multiplied by a -2. So the -2 times 3 to the x, that means it's being stretched by a factor of 2 and reflected over the x-axis. So we would take every y value and multiply it by 2. If we were to do that in green, if I were to multiply 1 by 2, he would be up here. If I multiplied 3 by 2, he would be up here at 6. If I were to multiply the 1/9 by 2, there'd still be 2/9. So take all of those points in green and reflect them over the x-axis. So instead of a +6, we'd be down here at a -6. +2 would be down at -2. 2/3 would be down here at -2/3, and 2/9 would be -2/9. So that is -2 times 3 to the x. But now we have to deal with our horizontal and vertical shifts. So we have -2 times 3 to the x plus 4, and that entire function is -1. So what does that mean? X plus 4 means we're going to shift left 4, and the -1 means we're going to go down 1. So remember, the change in x is going to be the opposite as what you think. +4 is actually left, but the y change, that d value at the end, works the way we want it to. -1 is down 1. So we're going to take all of those values in green, and we're going to shift each of those points left 4 and down 1. So over here at 1, -6, we're going to go left 4 and down 1. Try to make that dot big there. 0, -2, we're going to go left 4 and down 1, negative 2/3, 4 and down 1, and a negative 2/9, 1, 2, 3, 4, and down 1. So before I connect the dots, remember the parent function had a horizontal asymptote at y equals 0, which means if the whole function moved down 1, that includes the asymptote. So I have a horizontal asymptote here at y equals -1. That will help me when I draw and connect the dots for this function to know that I need to stay below the y equals -1. All right, on this last example, they're giving us a function that's graphed here, and it's a transformation of this parent function, y equals 2 to the x. Well, if we were to graph that parent function 2 to the power of x, it would be an increasing function. We would get 0, 1, 1, 2, 3, 8, and so forth. But we know it's not increasing, it's decreasing. So all of our x values have changed their signs. In other words, it's being reflected across the y-axis. So the first thing we know is that that exponent needs to be a negative or opposite of x to show that reflection. So if we focus on what our original is, if we were to reflect these across the y-axis, we would be here and here. Since they've given us this point and this point, I'm only going to focus on my 0 and my -1 at this point. Again, these 2 points right here. We're at a y value of 1 and a y value of 2. The frustrating thing is we know that our horizontal asymptote would originally be at y equals 0. But the graph that's being shown looks like we have a horizontal asymptote at y equals 3. So we know eventually we're going to have a shift of 3, but this is what occurs last. Remember, the last thing you do is a horizontal or vertical shift. If we just shifted up 3, we're still going to be, up here somewhere. We're not going to get to those points. So that means there is some sort of stretch that occurred. Let's kind of work backwards then. If we know that graph has been shifted up 3, let's shift it down 3 to see what our stretch would look like. If we moved this top left orange from -113 down 3, we would be here at 10, and our 0, 8 would be down here at 5. Okay, so that's what it would look like before that shift of 3. Well, I have a value here at 1 and a value here of 2. What would we need to multiply to move those 2 points of a y value of 1 and a y value of 2 up to a y value of 5 and a y value of 10? 1 times 5 is 5, 2 times 5 is 10. So that means we would need to multiply by a factor of 5 to move it up. So our final equation would be 5 times 2 to the opposite of x plus 3. It's always a good thing to check either by graphing it in your graphing calculator or doing an XY table to see if you do in fact get the points that was given. Well, the 2 points were at -1 and 0. So if we plug in a -1 to that equation, we would get 5 times 2 to the opposite of -1 plus 3. So that's 5 times 2 to the +1 plus 3, which does in fact give us 13. So that works. And if we plug in 0, we get 5 times 2 to the power of 0 plus 3, which is just 5 times 1 plus 3, which is in fact 8. This one was tricky because we saw one of the transformations, but it wasn't the first transformation that occurs. We knew it moved up 3 units because of the horizontal asymptote. So sometimes if you see the last movement, just reverse it to see what that middle movement would be. So there's our final answer for the equation, y equals. All right, guys, so that's it for 4.2, the graphs of exponential functions. If you have any questions, you know where to find me. See you soon. Bye.